Good morning. We are going to start today the program, the lecture on uncertainty. This is actually the part of the third module. We have covered now all for second and fourth module. Since the nature of the lectures are actually in connection, so I had actually made the fourth module first, and then the third module subsequently. Why it is because we are talking about an uncertainty situation where we had earlier introduced the possibilities of information asymmetry, etc. So that is why we have uncertainty placed in the fourth module, unconventional, of course. So in that sense, let us begin the discussion on this particular topic. Now, again, when you have the question of uncertainty, it is always important to know that in the real world of the earlier kind, in the first semester and all, we discussed everything based on certainty principles, like or the perfect information based scenario. And if there is a complete information asymmetry cases being dealt under the theory of firms, especially under the market conditions of a monopoly. So, other than that, normally we believe, or most of our theoretical proposition in the first semester largely been under the premise of certainty. That is, you have information, you have knowledge in the market, or no knowledge of the market, and buyers and sellers, they have information, etc. Now, once you have all this information, then you can basically have a sort of calculate the commodity which you are going to buy, or the price which you are going to uh, mm, pay for, etc. So but unfortunately, in the real world situation, when you want to see the real world price or commodity quantity, it is always happen comes with the possibilities of uncertainty. And this uncertainty is actually the situation where you have no capacity, or you can't even predict what is actually going to happen in that sense. So there is a complete information asymmetry on what is going to happen the next. So this is what is actually deals under the typical structure of uncertainty. But at the same time, we have our also issue of risk and all. When you have the probability being calculable, then you can say that the uncertainty can be changed to, or can be transformed as risk. So that is actually the important difference between uncertainty and risk. When you have a calculated the probability can be calculated, or the uncertainty in a probabilistic term can be calculable, that is the level of risk, level of things are calculable, then you call that possibility as a risky possibility. And you, based on the degree of risk and all, you can make decision. But in the case of uncertainty, the information and probability calculation of uncertainty is actually not completely given, or it is basically out of context in that sense. So the probability of repetitive event happens is the relative frequency with which it will occur in that. So probability of obtaining a head on the fair flip of a coin is 1 by 2. But doesn't mean that when you are flipping a coin, if it is have two sides, what would be the possibility is 1 by 2, because there is two side, either it turns to be head or tail, or in the x side, or the y side, in that sense. So if a lottery offers an indistinct prizes, and the probability of winning the prizes are in that context, you can calculate. That is even these are actually comes also with the possibilities of finite infinite case, but we will not discuss at this point the finiteness or infiniteness of this thing. So pi I, in that sense, when winning a prize r, a pi I, which is I is equal to 1n, then you can say that the probability of winning a lottery is the summation of all possibility of some of all possibilities of all this pi I, which is equal to 1 in that sense. So if that is given, then expected value of the same can be calculated with the following mechanism. For a lottery x with price x1 to xn, and the probability of winning is pi 1 to pi n, the expected value of lottery is going to be ex, which is equal to pi times x1 plus pi 2 times x2 plus pi n times xn, etc., etc., pi n times xn. So this is what is actually forms the kind of an expected value of that particular incident, or you can say about the lottery. So that in a nutshell, you write it as ax, which is equal to summation of all pi xi, summation of all pi I xi, in that sense. So the expected value is a weighted sum of the outcome in that sense, and the outcome, the weights are the respective probability in this context. All right. So once you have this thing, then you can have a calculation of the real world kind. Suppose if Smith and Jones decide to flip a coin, then you can say that head is actually x1, and that John will play Smith $1, and the tail happens then x2, that is Smith will pay John $1. So if that is the case, from Smith's point of view, for Smith's expected utility or value is actually the pi 1 x1 plus pi 2 x2, which is nothing but 1 by 2 of dollar plus 1 by 2 of the other percent dollar. That is the gaining dollar is with that of the losing dollar. So which is equal to 0 in that. So the games which have an expected value 0, that is the cost their expected values, are called actuarial fair game. So in this case, there is this kind of a game is called the actuarial uh, fair games, because one's gain is actually the other person's loss in that sense. A common observation is that people often refuse to participate in actuarial fair games. So this is another observation which is made in conceptually, and people are generally unwilling to play fair games. Why? Because in the fair game, what I gain is actually what you are losing. So I oh, and vice versa. What I am going to lose is actually going to be gained by the other. So the actuarial fair games are less attractive for people, and there may be a few exceptions when very small amount of money are at stake, when there is utility derived from actual pay of the game, etc. So we will assume that this is not the case in the real world. So that is why this particular notion of St. Petersburg paradox got its relevance. Suppose a coin is flipped until a head appears. If a head appears on the nth flip, the player is paid 2 times n. So if or 2 of n in that sense, so 2 n dollar. That is, if you have x1 which is equal to $2, then x2 is equal to $4, and this x3 is $8, etc. It's in that sense a geographic progression. That is, if you have xn times, if you flip, then you will get a dollar n in that. The probability of getting a head in the ith trial is actually 1 by 2 times I in that. So if you have a pi 1 which is equal to 1 by 2, and pi 2 is equal to 1 by 4, etc., etc., you can have a pi n which is equal to 1 by uh, 2 times n. In that sense, 2 squared, no sorry, 2 times n flip in that sense. So when you talk about this thing, the expected value St. Petersburg paradox game is actually infinite in that sense. So when you have this thing, then you normally write your ex, that is your expected value, as equal to the summation of an infinite possibility, that is summation of all pi I xi, which is equal to summation of all I powered, so it's 2 powered I times 1 by 2 of I. So this is what is actually the expected value. That is your expected value, which is equal to 1 plus 1 plus 1 plus etc plus 1 plus, which is actually infinite, because no player would play a lot to play this game. It is not worth its actually infinite expected value in that sense. So once you have a value of expectation is infinite, then people have a reservation of playing in that sort of a game. But still there are games which we know that, people, though the moves are infinite, but still people play. I'll come to that later. So expected utility, that is individual do not care directly about the dollar value, the price. Now when you speak about this expected utility, the money value people perhaps don't take into consideration, but doesn't mean that it is always going to happen. That so they care about the utility that the dollar provides. So not the face value, but the utility they are getting out of it. And if we assume diminishing marginal utility of wealth, then St. Peter's game may converge to a finite expected utility value case. So this would measure how much the game is worth to the individual in that. So if you have this thing in mind, then the expected utility can be calculated in the same manner as expected value. That is your EX, which is equal to summation of all pi of UXI. That is nothing but the utility which you are going to derive from the consumption of the commodity X times the probability which you calculate in that. So because a utility may rise less rapidly than the dollar value, the price, it is possible that the expected utility will be less than the monetary expected value. Now, this was basically and originally introduced by John von Neumann and Morgenstern. So they had in their book, this was introduced in 1944, and this is also forms the Neumann-Morgenstern's theorem. Suppose that there are n possibility prices that an individual might win, that is, you have an x1 to xn case. So arranged in an ascending order of the desirability, that is x1 least preferred price, that is your ux1 in that sense is actually the minimal value, which is 0, and you have an xn which is actually the most preferred price, which have a utility which is uxn, which is equal to 1 in that. So you have a range of value. Now you have a minimum value which is 0 and a maximum value which is 1 in that sense. So now the point of the Neumann-Morgenstern's theorem is to show that there is a reasonable way to assign specific utility numbers to other prices available. The Neumann-Morgenstern method is to define the utility of xi as the expected utility of the gamble that individual considered equally desirable in that. So that is, you have a uxi which is equal to pi times the utility of xn plus 1 minus pi I times ux1. So this is what is actually the proposition which they made, and since you have an uxn which is equal to 1 and ux1 which is equal to 0, which tells you that the range of value which you are valuing, and you have a uxi which is pi I times 1 plus 1 minus pi times 0, which is equal to pi I. That is your probability. The utility number attached to any other price is simply the probability of winning it, and note that this choice of utility number is arbitrary. So if that is the case, then the rational individual will choose among gambles based on their expected utility. The expected value of the von Neumann-Morgenstern utility index is actually been calculated from that. So in order to calculate this, let's consider two gambles. That is, the first gamble offers x2 with the probability of q and x3 with probability 1 by 1 minus q. So once you have this thing, then utility of first one can be derived. Let's just like the equation says, that q times ux2 plus 1 minus q times utility of x3 in that. So that is ux3. So second gamble offer an x5 with the probability of t and x6 with the probability 1 minus t in that. So your expected utility naturally turns out that for the second case is t times ux5 plus 1 minus t times ux6. So substituting the utility index number given number gives expected utility of first as your q times pi 2 1 minus plus 1 minus q times pi 3, and you have an expected utility of second which is t times pi 5 plus 1 minus t times pi of 6. So the individual will prefer gamble 1 to gamble 2 if and only if the difference is greater. That is your q times pi 2 plus 1 minus q times pi 3 is greater than t times pi 5 plus 1 minus t times pi 6 in that sense. So if individual obey the von Neumann-Morgenstern axioms of a behavior in a certain situation, they will act as if they choose the option that maximizes the expected value of their von Neumann-Morgenstern utility index. So this is a very important aspect of expectation calculation, or what you call the risk calculation of making a decision in that sense. So we expected utility theorem got its relevance because of these things. Now let's move towards the other problem of risk aversion, the behavioral aspect of how people respond towards such uncertain or risky situations and that. So two lotteries may have the same expected value but differ in their riskiness. Flip a coin that is for $1 one or versus $1,000. So once you flip a coin, you can also flip the coin for a small amount or a higher amount, as we have already talked about. Now, your risk refers to the variability of the outcome of such some uncertain activity in that sense. So when faced with the two gambles with the same expected value, individual will usually choose the one with the lower risk in that. So risk aversion in that sense in general, we assume that marginal utility of wealth falls as wealth gets larger. So in that sense, so a flip of a coin of $10,000 promises a small gain in utility if you win, but a large loss in utility if you lose in that sense. So a flip of coin $1 is inconsequential, as the gain in utility from a win is not matched with a different as drop of a utility from a loss of a smaller amount in that sense. So now this is in fact makes you to form a probability and wealth curve in that sense, probability based wealth curve. That is your UW is a fields about each value of the wealth. The curve is a concave to reflect the assumption that marginal utility diminishes as wealth increases in that sense. So you have this curve, and suppose your W star is the individual's current level of income, UW star is the individual's current level of utility. Now, if that is the case, then you have a UW star and W star on the contrary. And suppose that the person is offered two fair game, that is a 50-50 chance of winning or losing of $1 each, which is going to form the equation UHW star, which is equal to 1 by 2 times UW star plus H plus 1 by 2 of UW star minus H. Remember the earlier equation of the Neumann-Morgenstern index. And 50-50 chance of winning or losing in the second case, which is actually 2H, which is U2H of W star, which is equal to 1 by 2 or times UW star plus 2H plus 1 by 2 of UW star minus 2H in that sense. So this is actually going to give you a kind of a loose in that sense. So we can actually point at the expected value of a gamble of the first kind. See, look at the expected value, and if you are making the according to the first case, you are losing a smaller amount in that. So that is your W star was actually initially the first point, and if you lose, your wealth would be shifting towards the left, and if you are gaining, it would be actually on the right. So W star in that sense, the UHW star and the other thing, that is the W star minus H and W star plus H is given, and but if in the second case, if you look into the second case, the level of loss is actually much greater. So the first case, your level of loss is a smaller uh, one, whereas in the second case, it is actually even double or triple than what you are doing in that sense. So if you are losing, then you are losing a lot, and if you're gaining a lot. But at the same time, you are mm, uh, incremental benefit is smaller in that sense, and your preference is always play for a smaller risk for a risk averse individual. So this is also gives a kind of how you respond basically towards a different level of risk. Now, whether you are a risk loving person or risk averse person, risk neutral person, etc., would be given by this kind of a calculated move which you make. So most of the time this is also true in the stock market and other realm where people play. Many people play in a fixed interest game, whereas many had actually interested in derivatives and as futures, etc., where the element of risk is very high, as well as the level of gain and the loss in that kind of gambling is also very high in there. So that will tell you that what kind of an individual you are dealing with, whether you are dealing with a risk averse person or a risk loving person. Now, if it is a risk averse person, then UW star is greater than UHW star, which is greater than U2H of W star. So, if you are so loving a risk, then this person would be actually going for U2HW star, whereas the risk averse person is always go for UW star. That's it. So the person will prefer current wealth to that wealth combined with a fair gamble. The person will also prefer a small gamble over a large one if the person is risk averse. And the person might be willing to pay some amount to participate in gamble. Therefore, they have insurance premiums, etc., being paid in order to ensure that they are not being cheated or they are not going to lose much in that. This helps to explain why some individual purchase insurance and all. So even this is true when it is comes to the part of the government also, because many people, why people are supporting governments, and you believe that the supporting government is through paying tax, etc., gives you a kind of a third party support if there is any issue. For example, there is a policing, there is a court, there is all other kind of facilities being provided by the state in that sense. So immediately any problem occurs, then you are actually paying to the state in that sense. So now once you want to actually privatize all this thing, then things are going to be different in that sense, and the sentimentality of that individual in that particular society is also going to change in that sense. So the same logic you can also apply here in the private individual case, especially when you deal with the insurance and the attitude of the people towards their risk loving or averse nature or neutral nature. So in this particular assumption, what you are actually going to pay as a premium is the difference, the small amount, where you are actually ensuring that you are not going to be falling towards that W star minus H or W star minus H, where you pay a smaller amount in order to prevent that you are going to lose a lot. So you move even if there is a accident takes place, then you are moving from W star to W double dash. So the individual will be willing to pay up to W star minus W double star to avoid participating in the gamble and that. So still you are in the wealth trajectory where you are not losing much in that sense if you are so risk averse in that sense. So an individual who always refuse fair bets is said to be risk averse in that sense. So will exhibit diminishing margin utility of income, will be willing to pay to avoid taking fair bets in that sense. So consider a person with a current wealth of say $1 lakh who faces 24% chance of losing his automobile worth of $20,000. Suppose also that the person who wants Neumann-Morgenstern utility index is UW you have a UW which is equal to ln W. So once you have this thing, then the person's expected utility will be your EU, which is nothing but the 0.75 U times 1 lakh plus 0.125 U times 800, because the other is actually a losing thing. So EU, which is in that sense your expected utility is going to be turn as like 11 point 45714. So in this situation, a fair insurance premium would be $5,000, which is actually 5% of or 25% of the $20 in that sense. So the individual will likely to be willing to pay more than 5,000 to avoid the gamble. How much will he pay in that sense? So again, you can look the same thing with the help of the expected utility. That is, you have a U which is equal to U 10 1 lakh time minus x, which is equal to the ln 1 lakh minus x, which is nothing but 11.45714, and this 1 lakh minus x, which is equal to the e of this case, which is actually 5,420. So the maximum premium which one can actually afford in this particular case is $5,426. So this is what is actually the kind of index. If you, so any amount which is less than that, people will go for it if they are risk averse in that sense. If any amount which is exceeds that, people will not buy it and they will go for actually the kind of risk, because the price would be greater in that sense. Maybe smaller incremental difference and all will not be. For example, though this is a calculated thing, if they put a 5,500, also people will be indifferent technically, but this is also a matter of, but this is actually the exact amount once you have a calculation of that thing. Okay, so in the real world also people do have this sort of a calculation in that sense. So it is therefore very important to measure the risk in that. So most commonly used risk aversion measure was developed by Pratt, where Pratt's equation is RW, which is equal to the inverse with minus U double dash W by U dash W. For a risk averse individual, U double dash W is less than 0. That is, RW will be positive for risk averse individual, and RW is not affected by which Neumann-Morgenstern ordering is used in that sense. So Pratt measures of a risk aversion is a proportion to the amount an individual will pay to avoid a fair gamble in that sense. So let us H be the winning from a fair bet, that is EH, which is equal to 0. Let P be the size of the insurance premium that would make the individual exactly indifferent between taking the fair bet H and paying P with a certainty to avoid the gamble. That is, you have a EU W plus H, which is equal to UWP in that sense, UW minus P in that sense. So we now need to expand both sides of the equation using Taylor series. That is, because of a P is a fixed amount, we can use a simple linear approximation to the right hand side, which is nothing but the UW minus P, which is equal to UW minus PU dash W plus the higher order terms. So now for a left hand side, we need to use a quadratic approximation to allow for the variability of the game, that is H. That is, if you have a expected utility of W plus H, which is equal to expected utility W minus U HU dash W plus H, the second one, H2 uh, by 2 U double dash W plus higher order terms in that. So you keep extending this thing, then you will get this thing. So remembering that EH, which is equal to 0, dropping the higher order terms, the substituting K for EH2 by 2, we get an equation of this kind. That is, you get an identity, approximate identity, that is U W minus PU W Pu dash W, which is equal to or approximately equal to UW plus KU double dash W, which is actually what is the Pratt's case. That is approximately, this is the ratio of Pratt, that is KU double dash W by U dash W, which is KRW. So now the risk aversion thing I will discuss in the next lecture. Thank you so much for listening.